Thank you. Good afternoon, everyone. First and foremost, I would like to thank the organizers for this great conference in the beautiful city that is Novi Sad. I will be talking about work that I've performed in the past 4 years, and therefore I will be necessarily not going too much into the details. However, throughout the presentation, I will give references to publications where you can find more details, and of course, you're always welcome to ask questions after the talk. So I would like to start with a great quote from the Russian folklore. If you don't have a dog, your neighbor can't poison it. So it may seem funny, but after all, it's a simple and effective way of reducing your attack surface. So what does that have to do with the Linux kernel? Well, the Linux kernel is very much like this Swiss Army knife, this giant Swiss Army knife. It is very futureful. It has everything that you would ever need, but that also means that it has many things that you will never really need. One of such things is the RDS protocol, the Reliable Datagram Sockets. As far as I know, this is used only by an obscure Oracle database. However, it is in the mainline kernel. There are other examples, such as the perf events framework. That's a very useful framework for performance monitoring of the Linux kernel. However, you might not need that in your production environment. Similarly, there's an alternative debugging interface, proc-pid-mem, which you might know of. The same thing goes for that as well. You might not need it in your production environment. And there's also Berkeley packet filters, which allow you to do advanced performance packet filtering within the Linux kernel. Similarly, there are cases where you will need that, including in performance and in production environments. However, it is not necessarily something you always need. So that's something that it would be interesting to remove from the kernel potentially. And the reason I'm mentioning all this is, of course, as many of you know, all of those features have had CVEs vulnerabilities in the past, which had publicly available exploits for the Linux kernel. So one thing that you might wonder is how popular those features are, and you can do actually something very simple. It's just to take your favorite web search engine and to look for the thing that you're interested in, for instance, Linux RDS protocol. And there you will see that pretty much all of the results, apart from the Wikipedia result there, is not explaining what RDS is doing at all, but rather explains the exploit itself. So that's an interesting thing by itself. You have similar results with other features as well. But all of that is nice, and at the end of the day, you want to say that there's a large attack surface for no reason, but we didn't clearly define what it means to have an attack surface or to have a large attack surface. So that's essentially the first question that I address. Is it possible to precisely define the kernel attack surface and then measure it? Once we do that, we can in turn develop kernel protection mechanisms whose attack surface reduction will be quantifiable. So we will be able to measure it and say, oh, this has that much reduction. If we tweak it in that way, we will reach this much reduction. And of course, we want this to be practical, not just theoretical stuff. So I apply this to the Linux kernel in practice. So in this talk, there will be 3 parts. The first part is about the quantification of the kernel. That was published at NDSS in 2013. The second part is about a method that we've developed at compile time to tailor a kernel that corresponds to the features that you exactly need. And the third part is doing essentially the same thing, but without needing to recompile the kernel. All right, so for the first part, we'll talk about measuring the kernel attack surface. And first, we need to define what the attack surface is. So quickly, in operating systems research, typically people will talk about TCB, Trusted Computing Base, and measure the TCB size in terms of lines of code. What that will often mean is people will go into the source code repository, run a tool such as slop count, to measure all the number of lines of code within the repository, and they will say, for instance, that the Fiasco microkernel has 15,000 lines of code, that Minix3 has 4,000 lines of code. And their point is quite clear, because when you compare it to Linux 3.0, which has 10 million lines of code, there's really orders of magnitude of difference. But now we are interested in the Linux kernel itself. And in the Linux kernel, we want to be very careful about how we measure the lines of code. For instance, what about source files that are never compiled to start with? There are many of those because there are configuration-dependent code in the Linux kernel. What about loadable kernel modules? Code that can be loaded at runtime, potentially automatically, on demand, when an attacker or user requests it. What about code that is not even reachable from the system call interface? For example, you might have a buffer overflow in the boot code, let's say when parsing the kernel initialization parameters. However, that doesn't necessarily matter, because if you're there as an attacker and you can control the kernel initialization parameters, you already have full control of the system. What about code that is only reachable by privileged processes? For instance, there's a system call for loading and unloading kernel modules, but if you find a vulnerability in the parser there, it's again not something that will be really exploitable in practice, because you need to be root to call that system call to start with. So we need to take care about all of these points when we measure the attack surface. And that's what I'm going to be presenting in the next few slides. So the general idea of the attack surface is attacker reachable code. And the reason I'm mentioning it is because often it's confused with attack vectors, which is rather basically the API, the entry points that you have into the program you're looking at. And the idea for us was to use the reachability over the kernel call graph. We generate a call graph of the kernel, and we look at which pieces of code are actually reachable for the attacker based on assumptions that we make on the attacker itself. Then once you've done that, you can measure it with traditional code quality metrics such as number of lines of code, CVEs, and so on and so forth. So I'll go through one example. So this is a graph. Each of the nodes here can be functions, for example, functions in the kernel, and each of the edges are calls from one function to the other. So you generate that statically. And then you want to introduce entry points, E1 and E2 here. Those can be the system calls, for example, that an attacker can potentially make. And you also want to take into account some important subtleties, such as code that will be checking for privileges. In the Linux kernel, there are calls to capable function, which will check whether, essentially, whether you're root or not. So this is what we call a barrier function. So once you have that, you can go through and do your reachability analysis. And here you will find out that these three functions are not reachable from these entry points, taking into account the barrier functions. And you obtain a subgraph of the kernel call graph, which you can simply call the attack surface. And then, as I previously mentioned, you just have to apply traditional code quality metrics, can be the number of lines of code here. And for example, in this example, we end up with 370 lines of code. All right, so let's summarize this. We start with our program source and configuration. In this case, the Linux kernel for a given configuration of the Linux kernel. From there, we derive entry and barrier functions, and we also derive a call graph, so functions and calls between functions. With these two, we can create a subgraph, which we call the attack surface, and by picking a nice metric, we can obtain a measurement that we can use later on for comparing different approaches and measuring the attack surface. Of course, you might wonder how we come up with those entry and barrier functions, and that's actually very important, because it's essentially what the assumptions you are making on the attacker, so the security model that you're taking there. So I'll be presenting two security models that we've used. The first one is the ISOSEC security model. So this is the running kernel here. You have the system call interface, the core kernel code, and also loadable kernel modules that have been already loaded into the running kernel. But there are also loadable kernel modules that can be on-demand loaded, that are simply drivers, and there are also, of course, other types of loadable kernel modules. So in this security model, we assume that the attacker controls an unprivileged application. That's typically the case if you're thinking of something like a browser escape. Somebody that tries to escape a sandbox browser application. They will try to find a vulnerability within the kernel to escape the kernel itself. So the application itself is unprivileged and has access to the system call interface. So those are the assumptions that we are making. So based on that, you will have a partial attack surface, so part of the code that constitutes the system call interface, the core kernel, and the LKMs that are already running will be within the attack surface. But you will also have some on-demand loadable kernel modules which will be in the attack surface, because code from those kernel modules can be loaded on demand if the attacker requests, and the kernel will happily load, for example, sockets such as RDS automatically when you start using them. So what that means with the entry functions is that we take the system calls. That's fairly simple. And for the barrier functions, we will take functions that are calling the capable function in the kernel, which checks for privileges. We will also remove all drivers and non-on-demand loadable kernel modules, because for getting the drivers kernel module to be loaded, you kind of need to put the corresponding hardware first into your system, which might not be a reasonable threat model. It might be in some cases. But in this assumption, we're saying that that's not what we're assuming. So that's also what we remove. We consider them as barrier functions. And there are also some other details that I'm not going into right now. You can look up the publications if you're interested, or simply ask me a question after the talk. So the purpose that we have there is to estimate the attack surface from an untrusted, unprivileged process, just like what you would have in a browser sandbox. So that's nice. There's a variant of the security model, which we call static sec, where we do everything the same way, except we assume that there are no on-demand loadable kernel modules. The reason is that in the Linux kernel, there's actually a syscontrol that you can enable in order to prevent kernel modules from being loaded automatically. So that would be something that you can compare against. Finally, we have the generic security model called GenSec, where we essentially assume everything could potentially be in the attack surface, everything that has been compiled when you compile your kernel. So the reason we do that is to, first of all, have an upper bound on the attack surface that you can possibly have on that system. And it goes closely to what people have traditionally used in the literature to quantify essentially the size of a trusted computing base. All right. So now that we can measure the attack surface, I will present one of the two mechanisms we came up with, which is called compile time kernel tailoring, which allows us to reduce the kernel attack surface by making use of the built-in configurability of the Linux kernel. All right, so what we want to do is to go from that huge Swiss Army knife to something more manageable. And what that means in our experiments is that you go from the 5,000 feature Ubuntu kernel to about 500 features. So that's for a use case where you will be running a LAMP stack, a Linux, Apache, MySQL, PHP stack. And as I said, the idea is that we will use the configurability that is in the kernel. Most of you are probably familiar with this menu, the menu config menu for the Linux kernel, where you can enable or disable or enable only as modules different features of the Linux kernel. And this is great. You could spend some time on that, or maybe a few days or months to get close to a minimal kernel, because there are about 5,000 features, and that's just for x86. And you would obtain something close to a minimum kernel. And you don't have to take my word for it. You don't have to trust me that it's fairly difficult to do. That's an email from Linus Torvalds to the Linux kernel mailing list, where he says that the questions for the configuration are too opaque and he has no idea which of them a particular distribution depends on, because he would also like to have something close to a minimal kernel configuration. So we solve that problem by automating the task in a way. We do that by collecting traces at runtime. What that means is that you need to know, and that's very important, you need to know in advance what your workload and use case will be. So what hardware you will be using that kernel for, can be also a virtual machine, and what you will be running with that kernel. So that's basically the assumption we make there. Once you know that, we want to obtain a tailored kernel for that use case. And we do that with those 4 steps. I don't know if it's easy to see on the back there, but we first start by running the workload that we're interested in and collecting traces from the kernel. We look at which functions are being called inside the kernel itself. From there, we can use the debug symbols to trace back to the source line locations, and basically the if-defs that need to be enabled in order for that code to be compiled into the kernel. Then we use a tool called Undertaker that will generate essentially the dependencies that exist in the kernel as a Boolean formula between the configuration, the kernel configuration itself, the if-defs that are in the code, and together with basically the values that we've collected from tracing itself, we can put them into the formula, Boolean formula, and we can put all of that within a stat solver and simply solve that and obtain one kernel configuration that satisfies the traces we're interested in. So when we do that, we obtain our tailored kernel by simply recompiling the kernel. And a fun thing to look at is to simply look at which source files are being compiled into the kernel. So in this graph, you will have on the x-axis, that's the number of source files that are getting compiled. And in orange, you have the files that have been removed from your base kernel compared to the tailored kernel, which is in blue. So you'll see that, for example, in drivers, you have 95% reduction in the number of source files that you end up compiling. And that's very nice, but as I said before, it's not because we remove source files that we are really doing a lot of useful work in terms of security, because it might be that those drivers are simply never loaded at runtime because you simply don't have the hardware for it. So we really want to look at the attack surface reduction that we achieve. So I'm going to show these results, but so that's with an evaluation with the LAMP use case. We also have another evaluation in the paper if you're interested. But first, I will start with perhaps something that you've been wondering, which is how good is this tracing phase? Because we will be tracing the applications and looking at how many features we need to be enabled over time. But it might be that we are missing some features if we don't trace enough, if we don't trace for long enough. So that's basically what we call a convergence rate for the tracing. You want it to converge quite fast because you don't want to be tracing the system for months. So this is the experiment we've performed. On the x-axis, we have the time after the system finished booting. On the y-axis, we have the number of kernel configuration features that need to be enabled in order to have a kernel that satisfies all those traces. And over time, we run different workloads. So after booting, we SSH into the server. You can see that this creates a little surge in the number of features that we need in that kernel. Then we simply request one web page from our server. There's a little surge there as well. And next, we perform a more intensive throughput, more intensive requests onto the web server with HTTP perf. And you can see there's a significant increase there. The reason is that this will trigger Apache to create multiple processes and to enable inter-process communication between those processes, and that means new kernel features. And finally, you will see that it stabilizes. And when it stabilizes, we run Skipfish. Skipfish is a web application security scanner from Google. And the nice thing about it is that it will have essentially a high coverage of your web application. It will go and try each of the different PHP scripts that you have with different requests, and therefore it will try out almost or close to as many code paths as you have in your web application. So this is nice for us because it allows us to test whether the traces that we have so far are sufficient. And it turns out that they are. So just about 5 minutes after the booting the system there, we have enough traces even after running Skipfish afterwards. All right, so the attack surface reduction results, we can make nice graphs like these ones. Your baseline kernel is already interesting by itself because although you would have 10 million lines of code in a normal Linux kernel distribution, if you run slug count on the 3.0 kernel, you have 6 million lines of code here. And the reason is that there are many, there's a lot of code that is simply not compiled into the kernel because of configuration dependence, and also because many of the code is architecture dependent. So that's already one interesting result. And you can see that a good deal of the code is in drivers as well, but there's also significant attack surface within other subsystems as well. The file system networking, sound, the core kernel, and also others. So you can compare that to our tailored kernel, which is a little below 1 million lines of code, which means an 85% attack surface reduction. But that's only in the generic security model where we assume that everything potentially in the kernel is within the attack surface, right? So if we go back to a model where we make assumptions based on what an attacker that has access to the system call interface would see, we go down to about 2.6 million lines of code. So that's already interesting by itself. Like if you're an attacker, you can't just find any vulnerability within the whole entire kernel and hope that it will be reachable. There's a good chance that if you do that, you wouldn't find a vulnerability that you'll be able to trigger. So you can compare that to what we obtain with the tailored kernel, and the nice thing is that we obtain a similar result. And you can also see that the reduction is not simply in the drivers, as we looked at before, but also in all of the subsystems themselves. For example, the sound is completely gone because your web server is simply not emitting any sound when you're tracing it, so it has been entirely disabled. All right, so that settles the second part, and we will switch to the third part, where we want to look at essentially the same idea, but doing it at runtime, trying to not recompile the kernel, and trying to have some nicer guarantees in a way, nicer results. So we want more attack surface reduction also. The reason for that is that we will be tracing and potentially preventing calls at function granularity. We will look at individual kernel functions, and at runtime, we want to say, oh, that function is not needed by that particular application, for example. So what that means is that we can also be application specific. So different applications will exercise different functionality within the kernel. So if you trace the kernel and look at different functions, you can essentially create views for each of the applications themselves, and have different views for each application. Of course, the challenges there, the first one is performance overhead, because we will be doing dynamic instrumentation of the kernel at runtime. So you want to come up with a way of not tripping up too many of your probes that you insert into the kernel. And the second is false positives, because we will be more granular, looking at each kernel functions. The tracing that you will do will not converge as quickly as the future granularity tracing that we mentioned previously. All right, so to give an idea of the problem with false positives, we performed this following experiment. We run on different machines, different applications for a duration of a bit over a year. So that's about, I think, 1 to 3 months in here. So within 1 to 3 months, you will have everything that converges. So on the x-axis, we have time on a logarithmic scale, and on the y-axis, we have the number of remaining kernel functions to be traced before we converge, right? So one thing that you see is essentially a long tail effect there, because this is a logarithmic graph. And what that means is that it's pretty bad in terms of false positives. You will need to wait like 1 to 3 months to converge to your full set of functions that will be necessary for a given kernel function. And the reason for that is there can be all sorts of conditions where different code paths are triggered. For example, a memory allocation that fails at some point, things like that. So we need to also think about that problem and find a way of addressing it in some way if we do this at runtime, and we've come up with some ways. So here's the 4-phase architecture that we have. The first one is a pre-learning phase where we will take all of the kernel functions that are available for tracing, and we will look at which functions are triggered above a certain threshold. And we will call those functions a system set there. So for example, that could be functions related to memory allocation. They're used so often that we really don't want to really continue tracing them. There would be no point. So from there we also obtain the rest of the functions, which are called the learning set. And this will go into the learning phase where for each workload that we're interested in, for each application that we're interested in, we will use, basically define a given analysis set for each of the applications. What that means is we will see which functions in the kernel are used for a given application under the workload that we're interested in. So this analysis set goes into the third phase, which will try to cluster those functions in a way that reduces the number of false positive, or rather increases the convergence rate that we have. So this is the clustered version that you can see there. And then you have the final phase of enforcement, where you actually want to prevent those functions from being, those other functions from being called for a given application. All right, so the two steps that are interesting here is the first step, which will be there for performance reason. This step will remove many of the kernel functions that are used very often in the kernel. And this is great because that means that we don't have the performance overhead related to instrumentation of those functions. And the second phase that's interesting is the false positive detection, false positive prevention phase. All right, so for the first phase, the pre-learning phase, as I said previously, we'll be looking at functions that will be hit above a given frequency that is dynamically computed, and we will ignore those functions later on. So to give an example here, we have the X4 file system, and the X4 file system will have this code to essentially allocate new blocks. And within this function, it will call another function within a loop. And this function ends up being called so often when we trace the kernel that it trips up that threshold. So that's a nice thing, because it means that we can remove that function and consider it in the system set and only trace that main function itself. And in this way, we obtain the attack surface reduction that we might potentially be interested in by removing that particular function, but still not having the performance penalty of tracing that function at each execution of that function. So that does help us reduce the performance overhead. In the analysis phase, we do some grouping of the functions. What that means is based on some criteria, we say that two functions in the kernel are essentially equivalent with respect to tracing. So one of the things you can do is basically don't do any grouping at all, but you can also group by file, which means that if two functions are declared within the same file in the kernel sources, we group them together. You can do the same thing with the directories where they're declared. And finally, we also do the same thing with k-means clustering over the kernel call graph. So functions that tend to call each other are clustered together. So with this grouping phase, we reduce essentially the false positive. Finally, another interesting phase is actually the enforcement phase. because it's actually quite tricky to do something once you detect that a kernel function that shouldn't be used is actually used by an application. The reason is twofold. First, there are false positives, as I mentioned before, that you might need to deal with. You don't want to really crash the kernel once when you have a false positive, because you would be reducing the security of the system. So that's not really an option. And second is that you will have shared kernel states, such as memory that will be allocated within the process of a given of a given process, but that will be used by other processes or other parts of the kernel itself. So if you would basically kill the process at that point, you might end up with memory leaks, you might end up with deadlocks in the kernel itself. So that's not really a possibility that you have. So we have essentially two choices for the enforcement phase. The first one is simply logging the violation. And that might seem a little bit disappointing, but in my opinion it's quite useful, because you will be having audit logs of essentially the suspicious things that have been triggered in your kernel. And once you realize, for instance, that something went wrong and that your system was compromised, you can go back into those logs and say, how long has this been happening? What is potentially the kernel exploit that the attacker took advantage of? So that's something that's actually quite useful in my opinion. The second choice that you have is to essentially switch, once you detect this anomalous behavior, into a hardened mode of execution of the kernel. And we have a paper at CCS that will be presented in November this year, and I will give a quick overview of what we've done there. So instead of traditionally building the kernel, we build the kernel, each of the objects that are comprising the kernel, in two versions. The first version of the kernel is built as it would normally be, and the second version is built with hardening features enabled into the code itself. So we put these two together with a modified build system that we have, and that enables you to choose at runtime whether you want to run in the hardened mode or not. For example, you could do something as simple as to prevent stack exhaustion vulnerabilities, where you will be overwriting the thread infrastructure in the kernel, for example. Well, each time the stack is decremented, you just check whether the stack pointer is below thread info or not. That would be one thing that you can do in those hardened functions that you compile separately. So the nice thing about that is that you can have those potentially very costly hardening features that only get enabled when something anomalous happens. What that means is that during your normal use of the system, there will be no performance overhead that you will observe. So that's one way you can do the enforcement. Okay, now I will talk about the evaluation results we obtained with a workload on a Red Hat machine, which is used as a development server for a total observation time of 403 days. We've looked at the SSH daemon. We've looked at the network time protocol, which is an interesting use case because it will be exposed on many servers on the internet. We've looked at MySQL server, and we've also looked at the QEMU daemon for KVM, which is running in user space. All right, so for each of these applications, we've plotted a dot on this graph, which on the x-axis has the attack surface reduction that we measured in the static site security model in terms of lines of code. So that's a percentage. And on the y-axis, we have the convergence time compared to as a percentage of the total observation time, so the 403 days. So what that means is that if you're on the lower right-hand side of this graph, your application is, well, your attack surface reduction technique is really good. Okay, so for each of the applications, we have a dot, and we have also different colors for the different grouping techniques that we've looked at, so we can compare their effectiveness thanks to the way that we've been quantifying attack surface. For instance, we can see that when we don't perform any grouping, well, of course we obtain the highest attack surface reduction because it's the most granular approach, but we also have a very high convergence time. You might think of doing file grouping, and you do gain a little bit in terms of convergence time in some cases, but overall it's not really interesting because it just seems like you're reducing the attack surface reduction without gaining much in convergence time in general. You can make a similar comment with cluster grouping actually. You can see that if we use k-means clustering over the kernel core graph, we will have a method that will obtain the same attack surface reduction as directory grouping. However, it converges much faster. It converges almost 2.5 times faster than the file or no grouping case, right? So that's also something interesting that you can do once you've been quantifying the benefits that you have. All right, so with that, I would like to wrap up. In this talk, we've seen that the kernel attack surface can be quantified. And this is useful because it allows us to evaluate the effectiveness of a given mechanism that you come up with. So you can guide your research and your development in a way that allows you to reason objectively about which mechanisms are superior to others. We've also seen that the kernel attack surface reduction techniques that we looked at are effective in preventing kernel exploits. So for instance, for compile time tailoring, you would prevent with the attack surface reduction that we looked at about 285 out of 485 relevant CVEs within the ISO security model, and of course, for well-defined use cases. So that's a bit the limitation of that compile time tailoring approach. We need to know in advance what you will be using your system for. However, that is reasonable for things like embedded systems, where people will just be putting Linux on and leaving it there and never even updating it, right? If you're not satisfied with that, you can also look at the runtime approach, which does very high attack surface reduction. We've obtained 184 CVs that would be prevented out of 262 in the static sec security model. Essentially, it's more flexible because you can decide which applications you're interested in. It also has higher attack surface reduction, but also slower convergence rate. Remember that the compile time version converges in 5 minutes. The other takes 1 month or 3 months, depending on which grouping you're using. And both mechanisms are practical in the sense that when you run performance measurements, I didn't put them in this presentation, but I also have them if you're interested, I can show. You obtain no overhead or no significant overhead, basically less than 1% over any workload you would be interested in. And it's also non-intrusive in the sense that we're not going and saying we're modifying the kernel source code, we're just using the features that the kernel developers have developed, such as the built-in configurability of the kernel or instrumentation provided by kprobes. All right, so this settles my talk, and these are references where you can look at more details on the papers. Any questions? Yeah, go ahead.
It's mechanisms like kpath and kgraph for early time disable of functionalities of the kernel that are currently running, disabling functionalities that you don't need anymore.
Sorry, could you repeat your question?
Have you looked at using kpatch or kgraph for disabling functionalities that you already have in the kernel without rebooting the machine?
Yeah, no, I haven't. However, so the use case for kpatch and kgraph is different, right? So you have a modification to a given function of the kernel, and you want to apply that without rebooting the kernel. Essentially, you would be in the same problem as we have with the runtime version, because once you're there and you detect that the function has been called, and it shouldn't be called by that application. The question is, what do you do? Even with kpatch or kgraph, basically you would have to write code that will deallocate all the memory that has potentially been allocated along the path, or also unlock all of the locks that you've taken so far along the path. And that's basically the toughest part. And it's not the problem of patching the kernel really, it's rather the problem of what do you do once you detect the thing. So I don't think it would help basically, but kpatch and kgraph themselves are useful in their own ways for the purposes they've been built for. Yeah. Sure.
What is the current plan, if there is a current plan, is there maybe a timetable for when we will see the compile time, got the name of it,
Yeah.
logic, when we might see that back in the build system of the current mainline kernel?
I don't know if it will be in the mainline kernel, however, you can find it online. We've released the code for the compile time version. You can download it and try it on your own system and run it. You just have to Google Undertaker Taylor, and you will find the software that you can try.
So there's currently no communication with the mainline kernel guys to see if this is maybe something that is useful to put into mainline?
No, we haven't really, but we did. I did present some of this work at the Linux Security Summit earlier, a few weeks ago. And there are some plans for potentially the runtime version. But the compile time version actually doesn't have to be integrated actually into the kernel. You can do it orthogonally pretty much. Yep.
First of all, I want to congratulate you on the great talk. It's been one of the best here.
Thank you.
Is the runtime version also released as open source software?
Not yet. Hopefully sometime soon, but it's not yet released yet. I would like to.
Can you share if anyone is using both of the techniques, the compile time and the runtime technique, in production? Meaning with techniques that also software?
Well, it's not there at the point where you can use it in a production system really, but hopefully it will be there sometime. Yep.
So you said you're tracing the system to see what's actually being executed and
Yeah.
key features are being called. Now there is a problem, and a case in point is actually IPv6, because there are a lot of applications that check if something is present in the system so they can use it, but they
Yeah.
don't actually need it.
Yeah, that's right.
Like, calling this, you actually leave the feature in the system.
That's right.
Yeah, how can you handle this kind of problem?
Yeah, so that would be an interesting optimization to think of. But actually, as we've seen from the results, even without that optimization, you obtain good attack surface reduction at the end of the day. So it's not necessarily a fundamental problem, but I agree with you. You know, there will be processes that will just try out something to see if it's available, and maybe they won't end up using it because they find that something else is faster or more well suited to their needs. But in the immediate, I don't think it's a huge problem.
And also, you said that initialization code is not in the attack surface.
Yeah.
I'm not sure what you call initialization code, because, for example, device initialization code is in the attack surface, for example, in the USB drivers.
Yeah. Yeah.
Because I use an external package just to plug a USB device which is poison.
Yeah, so you're right. It depends basically on your threat model, right? So when I was talking about the initialization code, I was talking about the system call bound attacker, where that's controlling an unprivileged process, and there you don't have the threat model where the attacker goes and inserts something into your device. But if we take that threat model, which we haven't considered actually, but you could do measurements with that threat model as well by just changing the entry points you're interested in. then, as you say, you would also have to consider the initialization code there. Yeah. Sure.
I think I'm going to make myself rather unpopular in just 2 seconds.
Just go ahead.
Have you tested this, have you tried to tailor a kernel which is running systemd?
Actually, no, we haven't. We haven't.
Because I would have been very interested to see how much more surface is exposed on a system running systemd. I mean, people can theorize
Yeah.
that this would be a very nice way of...
So actually with systemd, maybe the problem is more the attack surface of systemd itself than the attack surface of the kernel.
Sure, but
So it would be interesting to look at the attack surface of systemd, for example. Yeah.
okay, I might try it out on a systemd system to see how far.
Yeah, sure.
Thanks.
How do you build the call graph?
Oh, yeah. So we use two compilers, NCC and Framacy. NCC builds decent call graphs thanks to basically it will. The trick with building call graphs is basically always function pointers, right? NCC has good heuristics because basically it's been reasonably designed for that use case where it will create call graphs that take those function pointers into account. Framacy, we haven't been able to really get it to work nicely with the function pointers. However, it's still nice to get the call graphs in the other cases because there are some things that NCC doesn't handle well. And with both these call graphs, we just merge them and we obtain one bigger call graph. And we've looked at some traces and we know that it's the call graph that we obtain is basically reasonable to make measurements on. But that's not necessarily something that I would use, say, for control flow integrity or anything like that. But it would be nice to have actually tools that get released where we get good call graphs so that it would potentially improve the measurements that we obtain here.
And how do you define the barrier functions? Because obviously capable is not the only thing that you have to check for. And one other thing is there are places in the kernel where the barrier functions are not obvious, like if you have, for example, the latest pink exploit. You can create a packet that will exploit the kernel without actually needing to verify that needs more capabilities. It's simply using IOCTL.
But then it's good, and then it's in the attack surface, and that's what we're interested in. What type of other? I'd be interested if you have other cases of like barrier functions that you think should be there. But basically, when we looked at it, we put capable functions. We removed the drivers and the non-loadable functions, and we've also removed some stuff that we've figured out by looking at basically the pseudo file systems, where potentially the pseudo file system will have essentially writes, file permissions that will not allow you to open them, although there's no capable check within the kernel itself, so that's why we've removed them. And also maybe you need to be root to be able to mount a given pseudo file system such as debugfs as well, right? So that's basically what we've found, but if you think there's more, I'd be interested in knowing actually. No other questions? All right, thank you very much.